I said probably outside his class. If you got to go and teach him. Alrighty, guys. Good morning. Welcome back to Calc 2. I apologize in advance for the fan noise. That will quiet down. Excuse me, quiet down in the next few minutes. Today, we are going to charge further forwards. So we've been talking about methods of integration. You have learned integration by parts, which is probably the most important single method of integration that exists. It's surprisingly powerful. It is a valid research tool. We've also learned about trigonometric integrals, specifically the sine cosine integrals. We've kind of gone through everything that can happen there. We've also talked a little bit about the secant tangent integrals. Today we're going to talk more about secant tangent integrals, and I'll also introduce the concept of Trig Sub. Before we say anything, let me take a look at your homework due dates, because yeah, the trig integral homework is set to be due today. We really didn't get time to play around with enough secant tangent integrals. I asked you to finish up through number 26 by today. So you see in just a second, here I will show you, you can watch. I will extend this homework, the 7172 homework, which you're supposed to finish up to number 26 on by today, to Wednesday. Oh, we get on Friday too. I want you working on that shit past Wednesday. I'll push it to Friday. All right. So you can get in there and do those trig integrals, get everything knocked out. Hopefully you have finished up through number 26. But you have until Friday to complete that homework set now. All right. Let's do the thing. Some more good stuff. As always, is MAC2312. Section number is 004. That is a Calc 2 class. And today is the 13th of September, 2021. Today, we're going to do more trig integrals. Which is a continuation of section 7.2. And just when you thought you were going to get away from the trigonometry, the section after this is Trig Sub. And we will be looking at that today as well, section 7.3. So this is a trigonometrically intense class. And I want to remind you, if you are feeling a little bit uncomfortable with all the trigonometry, that you can come to our course in the modules. And I've got lots and lots and lots and lots and lots and lots of stuff for you to review your trigonometry. Very important that you do this. So algebra, trig review. And then when you come to the section here on 7.2, we've got lots of examples of integrals of trig functions. Some 3 blue 1 brown, which is a really cool application of trig integrals. But mostly, I think if you're looking for stuff to look at, this Patrick JMT stuff or this Paul's Online Notes stuff is very good. I think the 5 out of 6 and 6 out of 6 videos for these, you can find those once you click on any one of these. They'll be linked there. So please take the time, understand the trigonometry, right? I think it's not a bad idea. Before we begin, the essential. I haven't done this with your group yet. The essential trig identities. This is not everything you need to know about trig. These are just the identities that we're going to use again and again and again. You must know your unit circle. You must know the definitions and graphs of your basic trig functions and the inverse trig functions. But these are the identities we will be using a lot. They kind of fall into a few categories. This guy, sine squared theta plus cos squared theta equals 1, you know. And his friend, tan squared theta plus 1 equals secant squared theta. And their friend, 1 plus cotangent squared theta equals cosecant squared theta. All three of these live in one box. They're called Pythagorean identities. We use the shit out of these. constantly using these. Another important family of identities are so-called double angle identities. That's like sine 2 theta equals 2 sine theta cos theta. The cosine double angle identity can be written in a few different ways. Cos 2 theta equals, I like to think of it as cos squared theta minus sine squared theta, but you can swap the cos squared to the sine squared using this Pythagorean identity to get two other equivalent versions of that. Double angles for tangent, you don't really need. You can cook them up, but we don't use them that much in this class. The other ones we use a lot of the half angle identities. Cos squared theta equals 1/2 only 1 plus cos 2 theta. And sine squared theta equals 1/2 1 minus cosine 2 theta. All right. So these are the identities that we use constantly. You gotta know these, you gotta know them cold. Right? You don't want to be guessing about the double angle identity for sine while you're like 3 pages deep into a problem test or something. It's not gonna be fun. So make sure you know these. Make sure you know this. The best way to get to know them is to use them, right? I mean, you can drill them with flashcards and shit like that if you want, but the best way to get to know these really well is to just make use of them over and over and over again. Use them in solving problems. Every time you need it, write it down. It will stick. All right. We left off last time. Left off talking about integrals of the form some power of secant times some power of tangent. All right. And we did actually go through the strategy. I gave you kind of written out in words the strategies that we use for these depending on the powers of secant and tangent. If you want to refresh yourself, that stuff is in the textbook. As are the rules for the sine cosine integrals. Remember, sine cosine integrals, if there's an odd power, you're going to do U sub. If there is no odd power, you're going to beat the thing to death with half angle identities until it looks like something you know. That's what they're saying here. Secant tangent integrals. If the power of secant is even, then you can get away with subbing for tangent. And you'll be able to take those remaining powers of secant and write them as tangents. If the power of tangent is odd, then you can get away with subbing for secant, because you'll have a copy of secant tangent and the remaining powers of tangent will be even, so you can rewrite them as secants. And if neither of those are true, if the power of tangent is not odd and the power of secant is not even, that means the power of secant is odd and the power of tangent is even, then you're kind of fucked. Then you need to use, integration by parts, generally, looping integration by parts. All right. Let's see some examples of these secant tangent integrals. I think the friendliest ones are the cases where the power of secant is even. Those are not bad at all. So let's evaluate the integral of about secant to the 4 times tangent squared. So I ask myself, is the power of secant even? The answer is yes, which means I'm going to substitute for the tangent function. Because the derivative of tangent is secant squared, this even power here will give me 2 secants I can set aside. So how do you do this? Like I said, the long game is to substitute for the tangent function. In order to substitute for the tangent function, I need 2 copies of secant that I can set over there with dx. So that will leave me a secant squared here. Tangent squared x. And I set 2 of the secants over here with dx. Because I know when I sub u equals tangent x, du is going to be secant squared x dx. So I just set this aside. Then these remaining powers of secant, I can rewrite them as tangents, which is necessary in order to make that substitution work. Secant squared theta is tangent squared theta plus 1. So secant squared x is tan squared x plus 1. I'm going to have my tan squared x just chilling here, and then secant squared x dx. Right? Rewriting the integral in this way makes it very easy to see what to do. I've got a bunch of shit here just involving the tangent function. And over here, I've got secant squared x dx, which is exactly what you need to substitute u equals tan x in this. I'm going to make that substitution. U equals the tangent of x. Du is secant squared x dx, which is why we set aside that secant squared. If I make this substitution in this integral, it becomes integral of u squared plus 1 times u squared times du. This piece being the du. And this stuff, it's a polynomial. I know how to integrate polynomials, right? It's a polynomial in tangent, and I substitute, I get just a regular polynomial. The way we integrate things like that, we distribute u to the 4 plus u squared du. And now you can use your power rule to pick up the antiderivative. So u to the 4 power there gives me u to the 5 over 5 plus u squared. Integral of u squared by the power rule is u cubed over 3. It's an indefinite integral, so I tack on a plus c, and at the end I have to go back to the original variable. So this is the 5th power of tangent over 5 plus the 3rd power of tangent over 3 plus a constant. Any questions on this procedure here? I know we've had a weekend go by. It's possible that it's a little weird to see this step. Does everybody understand what I'm doing in this step? I've set aside the secant squared because I know my goal is to sub for tangent, which requires having a copy of secant squared. The big money move is rewriting this as tan squared plus 1. Because I cannot have secants like secant of x or any x's left over after I do the substitution. I need everything to be in terms of the new variable u.
And Professor, you can only do that substitution due to that secant is odd, like the exponent, right? That's what you were saying before.
We need the power of secant to be even in order to make this work. So here we started with secant to the 4. If the power, so the kind of philosophy here, if you're wondering like what's going on, why is that the strategy? If the power of secant is even, then I can take 2 of them away and still be left with an even power. That's the magic here. So when I take 2 of these secants away and set them over here, because I know they're going to be soaked up, what's left is another even power of secant. And anytime you have an even power of secant, you can always rewrite it as tangents. So when we come up with that strategy, when I say the power of secant is even, that means we're going to sub for tangent. What we're thinking in the back of our brain is that, okay, 2 of these will go away when I make the substitution. Since this is an even number, when you subtract 2 from that, you'll still have another even number. That's good because I can always rewrite an even power of secant as tangent stuff. And that's what we need, right? We need everything in terms of tangent because that's our u. So there's nothing magical going on here. It really is just regular old U sub. But we're using trig identities and we're kind of thinking ahead a little bit. And so the thing that told me to sub for a tangent, even power of secant. Other questions or comments on this one? Okay. The other nice case for the secant tangent integrals, so if the power of secant is even, Gucci, we're going to sub for tangent. If the power of tangent is odd, all is well, we will sub for secant. Let's see what that looks like. Let's do secant squared x times tangent cubed x dx. And you know what? We haven't done a definite integral yet today. Yeah, screw it. Let's do a definite integral. Let's do this from 0 to pi over 6. Definite integral or indefinite integral, the strategy is still the same. Here, the power of tan is odd. So my strategy is to sub u equals secant x. I know that's my goal, right? Because that's what the algorithm tells us. In order to make that substitution go through, you know, if you sub u equals secant x, du is secant x tangent x dx. So you need to set aside one secant and one tangent with the differential, and then try to rewrite everything that remains in terms of the secant function. So this will become integral 0 to pi over 6 secant x tangent squared x times secant x tangent x dx. I set aside one copy of secant tangent because I know I'm going to need that for my differential. And then I look at everything else that's left over and I try to rewrite it all as secants. This piece is good. This piece is not. So before I can actually make that substitution, all right, this says secant x and then tangent squared. Well, I know that identity, tan squared plus 1 equals secant squared. So tangent squared is secant squared x minus 1. And then we still have here our secant x tangent x dx. And now my integral is ready for the substitution. I've got the differential over here, and I've got everything in terms of the secant function. So I'll go ahead and let u be the secant of x, which means du is going to be secant x tangent x dx. And because this is a definite integral, I also need to change my bounds. When x is equal to 0, u is going to be the secant of 0. What is the secant of 0?
Is it 1?
It is, yeah, it's 1, right? Secant of 0 is 1 over cosine of 0. Cosine of 0 is 1. 1 over 1 is 1. So when x is 0, u is equal to 1. My new lower bound will be 1. When x is equal to pi over 6, I need to know what u is going to be. Well, u would be the secant of pi over 6. What is the secant of pi over 6?
Cosine of pi over 6 is radical 3 over 2, right?
Mhm.
So 1 over radical 3 over 2, so 2 over radical 3.
Very good. Very good. All right. So my old integral went from 0 to pi over 6 and was in terms of the variable x. My new integral is going to go from 1 to 2 over root 3. Secant x, well, that's u times secant squared x minus 1, that's u squared minus 1. And secant x tangent x dx, that's du. And once we've gotten to here, we're home free, right? I could give this problem to a Calc 1 student. They would distribute the u and take an antiderivative and plug in the bounds. It's great. Questions on how we get to here before I finish the problem? So everybody's going to nail these on the test, right? Let's distribute the u. Still have my integral 1 to 2 over root 3. This is u cubed minus u du, whose antiderivative. That's I'll write it as 1/4 u to the 4 minus 1/2 u squared. And this time we don't go back to our original variable. We don't plug back in for u. We don't write a plus c. It's a definite integral. We made a substitution. We just evaluate between these new bounds. Which means I'm going to plug in 2 over root 3 for u, and then subtract what I get when I plug in 1 for u. So this is 1/4 2 over the square root of 3 to the 4 minus 1/2 2 over the square root of 3 squared minus, when I plug in the 1, this is 1/4 times 1 to the 4, which is just 1/4. And this is just 1/2. We can clean this up. 2 to the 4 divided by the square root of 3 to the 4. What is that? Well, 2 to the 4 is 16. This is 1/4 times 16 over the square root of 3 to the 4. Well, that's the square root of 3 squared times the square root of 3 squared. It's 9. All right, it's the same as 3 to the 2 minus 1/2 times 2 squared is 4. Square root of 3 squared is 3. And then we've got a minus 1/4 and a plus 1/2 distributing this negative. Here, the 16 and the 4 can interact. Here, the 4 and the 2 can interact. 16 divided by 4 is 4, so this is 4/9. 4 divided by 2 is 2, so this is minus 2/3. And then you've got your minus 1/4 and your plus 1/2. It's not really worth our time to grind out this arithmetic. We can if we want to. So 1/4 is negative 2/2. So these two pieces here would be negative 2 over 2 plus 1 over 2, which is negative 1 over 2. Oh, wait, no, sorry. I said that all wrong, didn't I? This guy, I'm so sorry. This guy is 2/4. So 2/4 minus 1/4 is 1/4. Positive 1/4 from those. This guy we can multiply by 3 over 3. That's 6 over 9. 4 minus 6 is minus 2. So these two here come out to negative 2/9. Just triple check that because my brain is apparently not working. 3 6 over 9. 4 minus 6 negative 2. Yeah, so this is negative 2/9 plus 1/4. And then you could have a common denominator between those. I'm going to stop here, right? The arithmetic isn't the fun part. you get here, I'll give you credit for the problem. Questions up to this line. Okay then, so secant tangent integrals, not that bad, as long as you're in one of those two nice cases. If you're outside of one of those two nice cases, not so pleasant. Right? But we did see one of those. We saw the integral of secant cubed last week, right? That was a looping integral, and that falls into that nasty case for the secant tangent integrals. Let me show you one more. Kind of not so nice. I mentioned this guy the other day. I could ask you for the integral of secant x times tangent squared x dx. This is an unpleasant one. So the power of secant is odd, and the power of tangent is even. So this is that nasty case. Right? If the power of secant were even, I could substitute for tangent. If the power of tangent was odd, I could substitute for secant. Since I have neither of these things, I'm in trouble. What does this mean? This means looping IBP. Trig identities. And a healthy dose of crossed fingers.
I have a question. If the power of secant is even and the power of tangent is odd, what are you supposed to sub for?
Yeah, there's overlap there, right? That's like the case where the sine and cosine powers are both odd. So if the power of secant is even and the power of tangent is odd, that means you could get away with either. And you should ask which one will give me the simpler integral. Generally, I would say substitute for the larger power. So if the power of secant is like 50 and the power of tangent is like 3, then you're going to want to power tangent. Yeah, then you'd want to do the secant sub. On the other hand, if the power of tangent is large and odd, like 101, and the power of secant is 2 or 4, then you could get away with either, but you're going to definitely want to substitute for tangent there.
Thank you.
Of course, of course. So there's a suggestion in the chat to use a Pythagorean identity on the tangent squared piece here. And I think that's a really good idea. So you can jump right in with looping IBP. So options. You can do the looping IBP right away. You can start right in with the integration by parts. One way to do that is by choosing u and dv as follows. I can pick dv to be secant x tangent x dx because I know how to integrate that, and I can pick u to be the leftover stuff, which is just the lingering copy of tangent x. If you do this, then du is secant squared x dx, and v is the integral of secant tangent, which is just secant. Then after applying one run of IBP, we will get integral. I'll show you this whole thing. One secant tan squared x dx equals uv, which is tangent x times secant x, minus the integral of v times du, which is secant x times secant squared x dx. And now I can take this secant squared and say, okay, secant squared, that's the same as tan squared x plus 1 by Pythagorean identity, the second Pythagorean identity. And we get tangent of x times secant of x minus the integral of secant of x times parentheses tan squared x plus 1 dx. And these parentheses are important, right? For two reasons. You need to distribute the secant. We also need to distribute this negative. So anytime you replace a single term by something that has more than one term, you need to put it in parentheses. All right, distributing the secant in here will give me secant times tangent squared, which is good because that's what we had to start with, plus secant x times 1, or just secant x. Splitting up that integral and distributing this negative gives me tangent x times secant x minus the integral of secant x tangent squared x dx minus the integral of secant x dx. So distributing the secant, distributing the negative, and splitting up the integral takes this to these. And now you take a step back and you realize you've got here my original integral. And you've got here my original integral. The problem has looped. Some unknown thing is equal to tangent x secant x minus that same unknown thing minus the integral of secant x, which I know. So we can add this to both sides. And what you get is 2 integral secant x tangent x dx is equal to tan x times secant x minus the integral of secant, which is an integral everybody should remember, the natural log of the absolute value of secant x plus tangent x. And then divide both sides by 2.
Professor, why is it minus the integral of secant x dx? Wouldn't it be plus? Oh, you distributed the
Distributing
negative.
the negative too, yeah. So if we just distribute the secant in there, it'd be secant times tan squared plus secant. But then when you distribute that negative, both terms become negative. All righty. I left off the square here in the previous line. I'm sorry, I need a square there. So what we get is secant integral secant x times tan squared x dx is equal to, dividing both sides by 2, I get 1/2 tan x secant x minus the natural log of secant x plus tangent x. Close parentheses, and you need a plus c, so we wrote it as an indefinite interval. All right. So this is one option. You can dive right in with the looping IBP. No harm, it's good practice. You should practice your looping integration by parts, right? Everybody should do this, and the damped harmonic oscillator. Everybody needs to do that shit, actually understand it. The other option for solving this integral is to rewrite as a combination of secant cubed x and secant x, other odd powers of secant. So we could take our original integral. This is the end, right? We have, this is the end. Does anybody, you guys don't listen to the doors, do you? This is the end of that first solution, right? The other way we could handle this is by jumping in here and saying, okay, secant x times tangent squared x. Since I've done the integral of secant cubed, in theory, I know the integral of secant cubed, I could try to rewrite this in terms of the secant cubed integral. So tan squared is secant squared minus 1. So this is secant x times secant squared x minus 1 dx, which is the integral of secant cubed x minus the integral of secant x. All right, and then you split this up, you say, okay, that's the integral of secant cubed x dx minus the integral of secant x dx, and apply the result. Apply the result from last week, which is the integral of secant cubed looks an awful lot like this thing. It's just got a plus here instead of a minus. So at this stage, we could say, recall integral secant cubed x. Odd powers of secant tend to be integrals people memorize, right? Like we just remember that the integral of secant is ln secant plus tangent. It's not uncommon for people who use this stuff a lot to just say, okay, the integral of secant cubed, I know it. It's 1/2 secant x tangent x plus the natural log absolute value secant x plus tangent x, plus c. So plugging into this line, would give us the dot 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 thing. Integral secant cubed is this. I'm gonna leave off the plus c for now, and then minus the integral of secant x, I know is the ln of secant x plus tangent x. And I'll put my plus c over here. So this is the other way you can attack this problem. And in general, if you have an even power of tangent times an odd power of secant, you can always use Pythagorean identities on those even powers of tangent to expand the integral in terms of odd powers of secant. So for a lot of people who have to deal with these things on a regular basis, that's sort of the standard attack. Rather than thinking of them all as separate or different problems, which they really aren't, they're all intimately related to one another. You can think of any integral like this, where the secant power is odd and the tangent power is even, as being some combination of integrals of odd powers of secant, which tend to be exciting problems. Knowing this fact, having the integral of secant cubed in your pocket ready to go, yeah, it's not bad. It's nice. It's kind of nice, right? It does take up some space in your brain. It's not a small thing. And on the test, it won't really help you, right? I'm not going to give you a problem. It's lecture logic, right? I'm not going to give you a problem on the exam that, like, if you have the integral of secant cubed memorized, you get full credit. And if you don't, you don't. If I give you a looping integral on the exam, which I will, just writing down a memorized answer will not get you credit. Right? We haven't talked much about my philosophy behind scoring tests, but the free response problems on my exams are worth 10 points. The answer that you enter is worth 2 of the 10, right? Everything else comes from your work. So on the exam, when I do ask you to solve a looping integral, you're going to have to do the looping integral. You're going to have to write out the integration by parts. I'm not going to give you this problem, though. I'm not going to give you something that like tempts you to do this. But just in case you're wondering, what should I be thinking about? How should I be studying? This is worth storing in your brain, but only after you've gotten comfortable with actually doing the looping IBP, because it's not something that I'm going to test you on directly here. your memory of the secant cubed integral. Okay, so two approaches to the tan squared times secant integral, looping IVP, or rewrite in terms of odd powers of secant. And that really concludes section 7.2. So I know it's a little choppy having part of the lecture last Friday and part of it today. You may want to go back and rewatch the trig integral lecture from last Friday and make sure you're really comfy. The other thing you may want to do is take the time to read how the book describes these strategies. It's literally the exact same thing I said, right? But they're, I think the term I used was more granular. They say, if n is odd, specifically equal to 2k plus 1, then we can do this, this, and this. All right. Is everybody thoroughly sick of trigonometry yet? I hope not. I hope not, because the next section is about trigonometric substitutions. So integrals that look like this, where you've got a square root, and then underneath that square root, some kind of quadratic. If that quadratic is a perfect square, then you can cancel the square root. All right, if this is like x, or, 1 minus x all squared, if that thing factors like that, then those are easy to handle. If you have a linear factor outside the square root, then you can get away with problems like this by doing a U sub. But if you have a non-perfect square quadratic factor under a radical, and you do not have anything outside that radical that will allow you to do the U sub, right, the piece you need for the differential, then you're pretty fucked, unless you make a very clever substitution. And this is what they're showing here. So take a second to look just at this highlighted portion. If this x were a times the sine of theta, then x squared would be a squared sine squared theta. You can factor out the a squared, right? This is a squared minus a squared sine squared theta. You can factor out the a squared. The reason this is nice is because the thing that's left over, 1 minus sine squared theta, is the same as cos squared theta. That is your Pythagorean identity. Sine squared plus cos squared equals 1, just rewritten, solved for cosine. And then the square root of a squared cos squared theta, you no longer have any addition or subtraction under the radical. It's just multiplication. You can take the square root of those things separately. You get a times cos theta. And strictly speaking, it's the absolute value of cos theta, because the square root of cos squared, square root of anything squared, is the absolute value of that thing. But throughout this section, we're going to be assuming that the square root of cos squared, for example, is just cosine. So that's the quick and dirty intro to trig sub. You're going to take some non-trig integrals and make them trig integrals. And these can only be done this way. They are very, very hard to do otherwise. The motivating problem here is finding the area of a circle. The big idea is that expressions like the square root of 1 minus x squared, or the square root of x squared plus 4, or the square root of x squared minus 3, can be hard to work with. Because the square root doesn't distribute, right? Like the square root of 1 minus x squared is not 1 minus x. The square root of x squared plus 4 is not x plus 2. And the square root of x squared minus 3 is not x minus root 3 or anything like that. So if you need to integrate something like this, you can't get away with any of this shit. This is just not true. In some cases, you can get away with a U sub. But that would require having the little piece for the differential, like a 2x. Yeah, if I want to sub for this thing, the 1 minus x squared, then du would be negative 2x dx. I don't have an x floating around out here if this thing is in the integral on its own, so I can't make that substitution work either. So we need something new. Thus, if we want to integrate this stuff, we need a new idea. And it's trig to the rescue. Trig identities. We'll save the day. All right. So I think that's enough of an introduction. I'm going to give you the table that's in the book here in just a second, but first I want to work through a problem just to show you kind of how these can arise very naturally and how they can be quite hard unless you approach it well. The type of substitution we're going to be making here is a little bit backwards. You're used to saying, okay, my new variable u is equal to 1 minus x squared. In fact, let's do this integral so we can contrast them. Here I want to integrate x times the square root of 1 minus x squared. So I've got an x out front, and that's going to be really helpful. Because here, with that x out front, I can let u be 1 minus x squared. Du, like we said then, is 2x, negative 2x dx. And this integral, here's the x dx. X dx is negative 1/2 du. Maybe I'll even rewrite it like this. So I've got square root 1 minus x squared times x dx. And I know from this that negative 1/2 du is x dx. So this would become integral square root of u times negative 1/2 du. You can pop out the negative 1/2 and then do all the normal things, right? The square root of u is now just a power function, u to the 1/2 du. The negative 1/2 out front comes along for the ride. Antiderivative here, you add 1 to the power, divide by the new power. 1/2 plus 1 is 3/2. So this is going to be 2/3 u to the 3/2 plus c. And then finally you replace. So the 2's can cancel. You get negative 1/3 times 1 minus x squared to the 3/2 plus c, and all is well and good. But you see, without this x here, I would be in real trouble without that x out front, because that's a necessary piece for my differential. If you're still doing the thing where you solve this for dx, that's fine too, right? You would just have this x canceling with the x from the differential here. Without the x here, there's nothing to cancel or absorb the x term from the differential du. So you can't make this substitution without this x. Let me show you what I mean. Here's the integral without the x out front. If I try to do the same thing, du is still negative 2x dx. The integral of the square root of 1 minus x squared would still be the integral of the square root of u. But then when you solve this for dx, you get negative 1 over 2x du equals dx. So here you'd have negative 1 over 2x du. You can pop out the 1/2, that's fine. Pop out the negative 1/2. But then you still have the square root of u and then 1 over x du. And I can't do shit with this. Remember what we said over and over again in the first week. Anytime you make a substitution, you need to get rid of every instance of your original variable. I got to get rid of all the x's. And this x right here ain't going anywhere. You could come back here and solve this for x, but that's not going to make life any better. So this guy's a problem. We can solve u equals 1 minus x squared for x to try. Let's see, I add x squared to both sides, subtract u from both sides, and I get x is the square root of 1 minus u squared. So what would that do to my integral? Well, nothing good. So then this piece would become negative 1/2 integral square root of u times 1 over the square root of 1 minus u squared du. So, okay, now we've made the substitution go through, but we've made shit worse. This is worse than the original. Look at the original problem. It just had the one radical, the one term underneath it. We didn't have these two things to fuck around with here. This is worse. Than the original. Which is sad face. All right, we don't want that. We want things to get better. Hopefully we want to solve this integral. That's my goal, is definitely to say exactly what this integral is. And because this substitution that works so well in the other one, we think maybe it would work well here, but it just doesn't, right? This guy is a red flag. He's telling you right away something ain't right. And you can try to force it through, but when you force it through, first off, you're going to get a plus and a minus here when you take this square root. So really this should be a plus and minus. That's a problem. Also, the resulting thing is nastier than the original thing. That's definitely no good. So we really do need something else. And that something else is trig sub. So how does one solve? How does one do this? We're going to let x be sine theta. So it's still a change of variables. It's still a substitution. But notice that my new variable is inside this function, rather than like saying u is equal to some combination of my old variable. Now I'm saying my old variable x is equal to some combination of the new variable. So these are sometimes referred to as like backwards substitutions. But everything goes just the way you would normally do with a substitution. You need to take your differential, see how that plugs in. You need to change your bounds if there are any bounds. In this case, the differential is actually easier to handle than in U sub, right? When you do U sub, you take your derivative, you get your du, and then you need to look back at your original integral and go, okay, how am I going to get things to cancel? Well, here, you're plugging into an integral in terms of the variable x. Your dx right here is something you'll just be able to plug in for because you'll have it automatically in terms of your new variable. If x is sine theta, then dx is cos theta d theta. And under that substitution, the integral of the square root of 1 minus x squared dx is going to become the integral of the square root of 1 minus x is sine theta. So this is sine squared theta. And don't forget to plug in for your differential. It's not dx anymore. It's cos theta d theta at the end. But you see, I didn't have to worry about anything canceling or finding any pieces in my integral to match the differential. I just drop it in there. This is because it's a backwards type substitution where I'm letting my old variable be equal to some combination of the new variable. They're easier. In a very real sense, this is easier than U sub. Now, why is this nice? You might look at this integral and go, you're fucking nuts. That's way worse than what I started with. I want to go back and do this. Except if you remember your trig identities. 1 minus sine squared theta is cos squared theta. And the square root of cos squared is cosine. Now there is a little bit of bullshit here. The square root of cos squared, this thing, is really supposed to be the absolute value of cos theta. Right? The square root of x squared isn't x, it's the absolute value of x. The square root of -5 squared isn't -5, it's 5. But in this class, and you'll see in the real world most of the time, there's always a way to fix this if you need to. In this class, we will assume that the absolute values are redundant, that you don't need them. We're going to assume cos theta is greater than or equal to 0. And we'll always do this. And not just for cosine. Wherever needed to simplify things like square root of cos squared theta, square root of tan squared theta, square root of secant squared theta, whatever. Whenever I need to assume positivity to get rid of a square root of a square of a trig function, I'll do that. And I'll do it without writing it. And you're free to do that too. Now I claim that things really have gotten better. The square root that was giving me so much of a headache is gone. I'm allowed to ignore the absolute values because I said so. Feel free to appeal to authority there. John said we can ignore these. The truth is, if you're doing a definite integral and the bounds are such that cosine is not positive, you can always work it out as though they are, and then kind of look at the graph and figure out what piece needs to be handled carefully to make up for the sign issues. So this really isn't a harmful thing. So this is really cos theta times cos theta, or at least I can treat it like that. And from here, it's not too bad. Who remembers how to integrate cosine squared on its own? We did the 7-2 homework. This is like a problem from 7.2, right? It's just a straight trig integral. How do we do it? So this is like a sine cosine integral. The power of sine is 0, which is even. The power of cosine is 2, which is even. So you use half angle identities. That's the half angle identity for cosine. It's the only tool that you need to integrate cos squared. And then your antiderivatives come nice and clean. Integral of 1 d theta is theta, plus the integral of cos 2 theta d theta is sine 2 theta over 2. And you've got a plus c. Remember, the substitution we made was x equals sine theta, right? So in order to go back to my original variable, which I must do because this is an indefinite integral, I'm going to have to do some work. First, I know sine theta, that's x, but sine 2 theta, I don't know what that is. And this is where the double angle identities I said are so important are going to come in. So I'll do a few things in this step. I'm going to distribute the 1/2. Actually, let me split these into different steps because I don't want to get you into trouble. There's distributing the 1/2. Now I'm going to use the identity sine 2 theta equals 2 sine theta cos theta. That's the double angle identity for sine, right? So we needed a half angle identity for cosine here, and I need a double angle identity for sine here. You see how much we use these trig identities, right? And we used the Pythagorean identity earlier. Now we're a little closer. I need to rewrite this all in terms of the variable x. Well, sine theta, this piece at least, I know that piece is just x. 1/2 theta, this guy I get by solving this for sine theta, solving this for theta. So to plug back in for x in 1/2 theta, we solve x equals sine theta for theta, right? How do you solve this sort of thing for theta?
Arc sine.
Very good. Arc sine, or the inverse sine function. I prefer the inverse notation, so I'll use that. But if you want to use the arc notation, that's fine too. All right, so this piece is going to be 1/2 times the inverse sine of theta. Or 1/2, sorry, 1/2 arc sine of, not theta, x. Sine inverse of x. 1/4 times 2 is 1/2. Sine of theta here, I know is x. But what about the cos theta? I've got everything else now. Right, sine theta, that's just x. Theta, that's the inverse sine of x. But how do I replace this by some x stuff? That's how everybody always says it, right? To plug back in for x in cos theta, I need to draw a triangle. Right, I need to know the relationship between theta and x, which is that x is sine theta, and then somehow deduce the relationship between cos theta and x. There's also ways to do this with identities, but draw the triangle. All right, I know x is sine of theta, and I know that sine is always the opposite over the hypotenuse, right? So the opposite over the hypotenuse is equal to x over 1. So I can label, if I label this angle right here as theta, then the opposite of theta is x, and the hypotenuse is 1. So everybody agree that this is a triangle where the sine of theta is equal to x? Now I've got a missing side length here, call it b. And I know that b squared plus x squared is equal to 1 squared, right? Because this is a right triangle. So at the end of your trig sub problems, most of the time you're going to need a right triangle to plug back in for x. And in fact, I'll show you when I make these trigonometric substitutions, I put this right in the spot where we change bounds. It goes in the same little box with the sub and the differential. We solve the triangle. Here I'll see that b is the square root of 1 minus x squared. So that's the missing side length here, square root 1 minus x squared. Which means that cosine of theta, which is always the adjacent over the hypotenuse, is this over 1. Which is just that thing. Finally, now we're ready to write down our answer. I have 1/2 inverse sine or arc sine of x plus 1/2 x times the square root of 1 minus x squared plus c. And that's correct. That is the integral of the square root of 1 minus x squared. Kind of nasty, right?
Did I ask where you got the sine theta equals x over 1?
This is from the substitution. So remember at the very start of this, we made the substitution x equals sine theta. So what we're doing here is I'm using my original substitution to flesh out the relationship between theta and x. So that was our big step here, is making the trigonometric substitution x equals sine theta. It was something that I pulled out of my ass at the start of the problem. And in the future, I'll tell you where it comes from. But yeah, let's go back and take a look at the rest of the problem here. Here we go. So remember, this is where we started. How does one do this? And I claim that the way we do it is by making this substitution, x equals sine theta. And dx is cos theta d theta, we plug that in, and we're like, okay, it comes down to this. Work it from here on the next page. So I just copied this back down here because we didn't have it anymore on that page. All right. So this is how you do it. right? This is if you have an integral of a square root or an integral that involves a square root of something like 1 minus x squared or 4 plus x squared or x squared minus 9, all of those integrals are done either by U sub if you're lucky, right? If you're very lucky, then you can do those with U sub if you have the little piece outside that you need, like we did in the very first example problem here. But all the rest of those integrals, and believe me, they are plentiful, right? Just to find the area of a circle, you have to do this integral, right? This integral from 0 to pi over 2 gives you 1/4 of the area of a circle. Just to solve that problem, which was known to the ancient Greeks, we need this gnarly trig sub thing. So let me give you the Bible, right? This obviously, this is not a religious thing. I'm not a religious person. Please don't let me offend you with the use of the word. Here comes your Trig Sub Bible, right? It's the thing that tells you what to do. Here's the way I like to arrange this. If your integrand contains an expression of the sort I'll put here, then you make the substitution that I'll put over here. I'm going to use the variable u. Here, u is a function of x. Could be any linear function. So it doesn't just have to be like x, it could be x minus 1 or x plus 2. If your integral contains a square root of a squared minus u squared, then you're going to make the substitution u equals a times the sine of theta. If your integrand contains an expression of the form a squared plus u squared, then you're going to make the substitution u is equal to a times the tangent of theta. And if your integrand contains an expression of the form square root u squared minus a squared, so the variable stuff comes first, so they're being subtracted, then you're going to make the substitution u equals a times the secant of theta. And the reason for each of these is the associated Pythagorean identity. Here, a squared plus u squared is going to be a squared plus a squared tan squared theta, which is a times tan squared plus 1, which is secant squared, so it'll come out nice. This is what you need to remember. Right? The textbook has a version of this, and they show the related identity in the third column, and they show the specific range of theta values that we're allowed to consider here. This is the bare minimum that you need to remember, all right? So if you see something like this and you can't get away with a basic substitution, here's the trigonometric substitution you need to use. Let me see how I'm doing for time. We can do some more if there's time. This was 9:30 to 10:45. We are right out of time. So let me finish by setting up a problem for you, all right? And then we'll look at more of this stuff on Wednesday. Here, we can do this one. 9 minus x squared over x. Oh no, that's too similar. That's a sine sub. Fuck it. Yeah, we'll do it. Okay. So I look at this, I go, uh-oh, square root, quadratic stuff underneath it. Remember, that doesn't simplify. Can't just simplify that. It doesn't fucking work. So I look at my Trig Sub Bible. Does this radical look like any one of these? Well, what is it? It's 9 minus x squared. That's like a is 3, right? Square root of 9 minus, remember, u can be any linear function of x, just u being x itself is the simplest case. So yeah, this looks like the first row of my Trig Sub Bible, just with a equal to 3. So the substitution we're going to make here is x equals 3 sine theta, which means dx is going to be 3 cos theta d theta. If I go to plug this in, 9 minus x squared, under my radical, that's 9 minus 3 sine theta all squared. And downstairs there, x squared. Well, if x is 3 sine theta, then x squared is 3 sine theta all squared. And then dx, remember, is not just d theta, you need to replace this as well. It's 3 cos theta d theta. I'll just show you 1 or 2 more steps, and then I'm going to have to let you go because I have another class that starts right after this. And under my radical here, I have 9 minus, and then 3 sine theta all squared. That's 9 sine squared theta. Downstairs, 3 sine theta all squared on its own. That's 9 sine squared theta. And over here, I have 3 cos theta d theta. I can factor a 9 under that radical. And I have 1 minus sine squared theta. The 3 cos theta is still chilling over here, next to the d theta. Downstairs here is still a 9 sine squared theta. And here's the magical step, 1 minus sine squared. That's cos squared. So what is this? This is the square root of 9 cos squared theta, all divided by 9 sine squared theta with a 3 cos theta d theta chaser. Now, upstairs, due to this identity, we no longer have any addition or subtraction under the square root. So I can take the square root of the top now. This is what's so magical about Trig Sub. That addition and subtraction that was up here, was in here. Now it's just multiplication. So you can take the square root of 2 things multiplied together individually. That's fine. Square root of 9 is 3. Square root of cos squared is cos. All right, what else is going on up here? I've got a 3 cos theta. From the differential, I'll bring him up. And downstairs I have 9 sine squared theta. The 9 will cancel with the 3's. And you get cos squared over sine squared. We are out of time for today. So I'm going to leave this right here. Go ahead and finish this integral up. All right, go ahead and wrap this guy up. He's not at all hard. I'm not going to tell you what to do. It's a 7.2 integral. It's the type of thing you had in your homework. So please knock out the remaining bits of the homework from last week. That is now due for you on Friday of this week. I will be publishing later today your Trig Sub homework. That will be due next Monday. There will also be some 7.4 stuff in there. So that's it from me for today. I got to get running. I got another class that starts in just a few minutes. I hope that you found this illuminating. Trig Sub is really a beautiful thing, but you must put in the time. If you don't put in the time, you're going to be boned on this stuff. It involves a lot of different things from your trigonometry classes. Some of those things I know are not covered very well in every trigonometry class. So if you find yourself feeling at all insecure, uncomfortable, whatever, please come talk to me in office hours, send me a Canvas message, ask people on Discord, talk to the tutors, do what you need to do to get comfy here, because trigonometry is going to be a big part of this course, not just here, but in later sections as well. All right, that's it from me, guys. I hope you enjoyed this. I'll see you on Wednesday.